In this video, we'll consider aspects of probabilistic scenario analysis. PSA, or probabilistic scenario analysis, is actually a bundle of tools and techniques. It's not any one particular thing. But what it does is it combines the use of scenarios and probabilistic methods. Vibrio parahemolyticus and oysters and similar models are examples of probabilistic scenario analysis. In some of my U.S. Army Corps of Engineers work, they have developed tools for the entire agency to use. The Hydrologic Engineering Center's Flood Damage Assessment, Beach FX, Harbor Sim, these are all examples of corporate tools that have been developed on the basis of a probabilistic scenario analysis. We begin with scenarios. Think of scenarios as the stories we tell about a risk or an uncertain situation. Scenarios can be used to describe the present, but they're most often used to describe possible futures, situations that could exist, situations that might exist, situations that we would like to exist. Some common scenarios include the without conditions, with conditions, the base year, existing conditions, failure conditions, and so forth. One reason we use scenarios is because it can be very useful to compare them. Take a look at this simple made-up example. In the columns you find habitat units and cost. Habitat units are improvement in ecosystems. So one scenario would be the without condition. If we don't take any action, we will have 5,000 habitat units in the future. But if we take no action, it doesn't cost us anything. Now imagine that we have a plan A, so we look at the future with plan A in place. Then our habitat units increase to 7,500 and the plan costs us $1 million. The changes due to plan A are an increase of 2,500 and an increase of $1 million. It's usually differences in scenarios that we're interested in when we make risk management decisions. Imagine another plan, plan B, and that boosts us up to 25,000 habitat units, a change of 20,000. But this might be a $1 billion plan, and so we have a change in cost of $1 billion when compared to without condition. And so scenario analysis are very useful in particular because of the information that we can get from scenario comparisons. I like to differentiate three kinds of scenario analysis. One of them is monolithic scenario analysis. I may have invented that term. I've not encountered it in the literature. But this is where decision makers consider only one possible future. In the United States, our national health care program is called the Affordable Care Act. At the time that was being debated, we only looked at basically one future result from the passage of that act. Clearly that future has not been obtained, but that was a good example of using monolithic scenario analysis as a basis for decision making. Deterministic scenario analysis examines just a few specific scenarios, more than one, but less than the hundreds and the thousands that we've seen in our Monte Carlo simulations. We would use deterministic scenario analysis to organize and simplify this avalanche of data that we are faced with into a limited number of possible future states of the study area, the infrastructure, or the risk problem that we're interested in. Those states might include the best case, worst case, most likely case, for example. And then the third variation is probabilistic scenario analysis. We use this to characterize the range of potential futures and their likelihoods. So this would be the type of thing that we would use Monte Carlo processes for. Here are three common scenario types used in risk assessments. There's the as-planned scenario, failure scenarios, and improvement scenarios. The as-planned scenario is sometimes called the surprise-free or risk-free scenario. It's the story that we tell that is free of any failures of the components of our system. Every feature of the system functions as it was designed to function, so we end up with no exposure to the hazards. Take the example of a terrorist attack on infrastructure here, this simple model. If the plot's detected, yes, our system works as planned. If the plot is not detected, then we ask, is the attack foiled? If the answer is yes, the system works as planned. But if it wasn't foiled, then we say, is the structure undamaged? And if the answer to that is yes, our system works as planned. If we get no's to all these questions, that's a successful attack, and that would be an example of a failure scenario. Failure scenarios tell the story of how various elements of a system might interact under certain conditions, and they challenge the notion that the system is going to function as we planned for it to function. A very common failure scenario is the worst case scenario. Another common failure scenario would be a without condition, a future in which we fail to address the risks that we are faced with. A worst case scenario is kind of an interesting thing because it introduces this conservatism into our analysis. It is conservative in the sense that it tries to imagine the worst of all possible outcomes. So in a sense, you could think of that almost as a deliberate error being introduced into the analysis. There are limitations though, because given any worst case scenario, an even worse case can be defined. So you tell me the worst case scenario you can think of, and I'm going to throw an asteroid striking the Earth on top of it, and your worst case scenario just got worse. Worst case scenarios may be plausible. They may be based on plausible reasoning, and in that sense they might be possible. But possible is not necessarily probable. Just because you can imagine something doesn't mean it's likely that would happen. The other problem with worst case scenarios is that we find failure in the world in many instances that are better than the worst case scenario. So failures are possible with less than worst case scenarios, and a worst case scenario approach to decision making ignores that. Improvement scenarios are future oriented. And that's because risk analysis often results in new risk management options designed to reduce risks. So we develop an improvement scenario for each risk management option that we consider. And then we use them to evaluate risk management options. We would use these improvement scenarios to select the best option. The with condition is another name for a risk management improvement scenario. Here's a chance for you to hit the pause button and develop a scenario for how you become rich. Try it out. I mentioned earlier that scenario comparisons are often a desired output or outcome of scenario analysis. So we need to talk about that a little bit. Let's begin by considering some terminology here. The most likely future condition, absent any new risk management options, is called either the status quo or what I like to call the without condition. And this is a basic failure scenario. It's failure to act. Every new risk management option gets evaluated against this condition. So we stand here in the present and say, given what we know about these risks that we're dealing with, if we do not take any action, what does that future look like? And we call that picture of the future the without condition. There is a most likely future condition with specific risk management options in place, and we would call those futures a with condition. These are improvement scenarios, and there is a with condition for each risk management option that we consider. So for example, if we had 4 different risk management plans that we could implement, we would have 4 different with condition scenarios. Then the idea is to compare the with and without conditions for each new risk management option. Let's illustrate that with a picture. So we begin here with time on the horizontal axis and some risk effect on the vertical axis. This is a stylized graph. It could have been drawn in many ways. Notice I begin with the existing risk, that dot there that's at time 0. And if you assume that the future is going to look just like the present, that's the baseline there. Very often though, what happens is in the future, if we take no action, many of these risks that we're dealing with only get worse. And so that's what I've shown in this stylized drawing here, where the future no action is an increasing risk. We also have the possibility, of course, that we take action and the future with an option in place could reduce the risk as seen here, the future with option A in place. So now we have three different lines that are indicating paths, future paths, for risk effects. A before and after comparison compares the future with our risk management option in place to what we have now, the baseline, today. Before and after comparison is used a great deal in the United States for NEPA, the National Environmental Policy Act analysis. By far, the more analytically correct and rigorous comparison would be the with and without option comparisons shown here, where we compare the future, if we take no action, to the future with an option in place. And you can see there could be significant differences between the with and without and the before and after comparison. Before we leave this idea of comparing scenarios, there's a third method of comparison, and it goes by many names. I'm using gap analysis here. And the notion that I would like to put out to you is that with gap analysis, someone establishes a standard or a target, such as you see here. And then it is the risk managing agency's responsibility to try to hit and exceed that target. So what you see here, the future with option A in place, we fell short of the target here. And so we would do an analysis of the gap between what we were hoping to achieve and what we actually achieved. I could just as easily draw another line, future with option B in place, that would exceed or dip below that target line there. So this is another way that we can consider how to compare scenarios. Let's speak briefly about event trees, although we'll return to them in greater detail later in the course. Event trees are tools that we can use to structure scenarios. Here are some other scenario tools. Event trees use forward logic. Something happens and then we look at all the possible outcomes in an uncertain future. Fault trees use backward logic. We begin with a result. There's been a murder, and we work backwards from that to identify all the possible suspects. Decision trees are a bit different. In event trees and fault trees, every node is basically subject to chance. It is beyond our control. In decision trees, we do have opportunities to make decisions. And so we can get any pattern of decision chance that you could imagine in a decision tree. Probability trees are very much like event trees, with the exception that the only values that you find in them are probabilities. Here's a very simple event tree, and this is starting with a lockage. A lockage occurs when a vessel on a river encounters a dam. On one side of the dam, the water is very high. On the other side of the dam, the water is very low. So to navigate between these two elevations of water, the boat pulls into a lock chamber, and water is either pumped out of the lock chamber so it can go from high to low water, or it's pumped in to go from low to high water. So the problems that can occur would be a stall, that when you are entering into the lock, a stall occurs. That could be any number of things that prevents the lockage from proceeding normally. So if a stall occurs, that can be one problem. If a stall occurs, that's a good thing, but then there could be a delay for other reasons. And so we look at two different undesirable outcomes here. A stall occurs, a stall does not occur, but there is a delay for other reasons. And so we have a simple event tree here that begins with a lockage, and you see three different ways that this can turn out. Trees are composed of nodes and branches. You just saw the lock event tree. The circles indicate chance or probability nodes. These are events we have no control over. If they were decisions, we would make those nodes squares. The model ends in triangles, which are usually designating endpoints. You're going to be working with event trees, so I'd like to introduce this notion of tree time. The location of a node in a model represents a point in logical time. That might be different than chronological time. So when you see a decision node in a model, models beginning on the left and they proceed to the right. So when you see that decision node, that's the time when a decision maker makes a decision. The chance nodes, that's the time when the result of an uncertain, uncontrollable event becomes known. And an endpoint, that's the time when the process is ended or the problem's resolved. So we think about time or logic flowing from left to right. Branches that lead into a node have already occurred. Branches that come out of or follow a node have not yet occurred. And so when you look at a model, it might not be chronological time, because you will find when you work with these models that there's a good bit of leeway and sometimes confusion as to what order should you put things in. But when you do put things in order, you do establish a logical time in your model. The lines that emerge to the right of a node are called branches. Branches from chance nodes are possible outcomes of the uncertain events. You have no control over these. Branches from decision nodes are the possible decisions that can be made, and you can control those. Usually branches have values attached to them. Probabilities are listed on top of the node, and probabilities are conditional. The probabilities that values that you see assume that everything to the left, all the preceding events, have already occurred. The probabilities attached to the branches coming out of a node must sum to 1, as you know. If you have quantitative values other than probabilities, they are typically listed on the bottom of the node. My preference is to use yes and no branches when possible. It's not always going to be possible, and it may not be desirable. So you can actually have any number of branches coming out of a node, but if you use yes and no, you restrict it to 2, and it makes your model simpler, at least in that vertical dimension. We can separate the elements of a problem in a structured way when we construct a tree. Different trees developed by different people or different trees developed by yourself can yield different insights into a risk problem. Endpoints define the sample space in your problem. That is, all the possible outcomes of interest. So they must be mutually exclusive. If we are looking at the model and considering one example, there should be only one endpoint that you would arrive at. And they have to be collectively exhaustive. They have to include every possible ending. When you are designing a model, it's important to think about what the values or units of measurement will be for your endpoints, because you have to be consistent throughout the model. There can be multiple objectives in a model, meaning you could have probabilities, cost, lives saved, profits, any number of objectives. And when you have more than one, there may be a payoff matrix accompanying your model. Here's an event tree that illustrates the idea of the sample space we were just talking about. This event tree is modeling the toss of 3 coins independently. You see coin 1 is a head or a tail, and then coin 2 could be a head or a tail. But because there is a possibility of a head or tail in coin 1, there are 4 possible outcomes with 2 coins. And then if we toss a third coin, you can see the number of outcomes increases. What's important is in your risk assessment is to define all the endpoints that are of potential interest. Collectively exhaustive and mutually exclusive endpoints. Once you've constructed your model in this fashion, you can combine and count the endpoints that are of interest to you. For example, if we were interested in what the probability of getting 2 heads from the toss of 3 coins, we could now go through, count the total number of ways the outcomes can turn out, count the numbers that have 2 heads in them, and easily estimate that probability of obtaining 2 heads in a toss of 3 coins. You're not likely to encounter many problems as simple as tossing 3 coins, So constructing a model can actually be quite difficult. So we begin with the notion of knowing the question you're trying to answer, know the relevant endpoints, know what the answers look like, and then keep it simple. Keep your model as simple as possible. If you are trying to model the ways that a dam fails, maybe the very first model is there's rainfall and there's dam failure. Does a model that simple answer your questions? If it does, you're done. If it's not, then what you're going to do is you are going to gradually make your model more complex. So my point here is if you're dealing with a dam failure, there are so many things that could happen that if you try to think of them all before you begin your model, you may never begin your model. So don't attempt all the complexity of your model at once. Practice that rapid iteration prototyping. Get a simple model. Rainfall causes dam failure. Is there anything that happens in between that might be important? Oh, okay, well then let's start to put those details in. Is there anything that could happen before the rainfall that's important? Is there anything that happens after dam failure that's important? We can gradually make a model more complex. But you do want to make sure that all the possible endpoints and all the important pathways are included in your model. You'll need to learn how to analyze the pros and cons of the details, but you do that only after considering alternatives. Try not to fall in love with your first idea. In the model building video, we talked a little bit about detail. How much detail do you put into your model? Well, you need all the possible relevant endpoints and all the important pathways to those endpoints. But how much detail in the pathways or progressions through your model is really the question that we're after. More detail means more pathways means more data means more time and more money. So you need to ask, will a more complex model change the outcome values much? Or perhaps the extra detail means extra insight. So you're always going to struggle with this balance, the trade-off. So do you want a model that enables a good decision, or do you want a model of reality? We've been talking about scenarios and tools for structuring scenarios, and now we want to move to the probabilistic part of this probabilistic scenario analysis. So we briefly revisit the Monte Carlo process. Because of variability and uncertainty, there are many possible scenarios. The basic plot lines might be relatively limited, and you can structure those with trees or with process diagrams and things. But when we start to consider the values of the parameters and the inputs in those stories, that's when the numbers become unlimited, and it's not possible to describe them all. But some of them might be important to the decision process. So probability can be added to a scenario structuring tool in a variety of ways, and the one that we've been focusing on is the Monte Carlo process. Recall this simple illustration of a Monte Carlo simulation. A value is randomly sampled from one input, a value is randomly sampled from a second input, and then depending on the structure of the model, the equations and calculations that are built into the model, these two values are used to calculate an output value here. An iteration is a single calculation of a simulation, and a simulation is a collection of iterations. Here are a couple of takeaway points. Probabilistic scenario analysis is a class of tools that relies on scenarios and probabilities. So all the tools that can be used for scenario construction and comparison, and all the tools that can be used for propagating probabilities and uncertainties in a model are all part of this class of tools. Probabilistic scenario analysis takes many forms. Most risk assessments are some form of a PSA. Event trees and fault trees are common examples of PSAs. Process models and flow diagrams also are examples. So probabilistic scenario analysis are very powerful and useful tools.